at the end of the century. And so here's my interpretation is that most of the cities will grow horizontally under these scenarios, this urban sprawl pattern. On the other end of the spectrum is SST1, sustainability pathway. Here, we also expect fast urbanization, but urbanization is driven by sustainable living in compact urban form. And so we expect, I expect sort of cities to grow more sort of vertically. But regardless of the growth patterns, regardless of pathways, opportunities exist to transform, to re-engineer the urban landscape to a climate-friendly landscape by using high albedo material and high emissivity material. So this is a theme I will return in the later part of my talk. So that is basically the quick summary of the project being planned here at Yale. I'm eager to hear your feedback and comments at the end of the talk to maybe collaborative opportunities may emerge out of the conversation, collaborative opportunities. Now, let me switch gear and now turn to a case study. Some of the ideas I spoke about about that initiative can actually be traced to this case study. So this is a case study involving the city of New Haven. We call it City in Hot Waters. Essentially, this is a class I co-taught a few years ago with my colleague Brett Gentry, who is a professor of environmental law and policy. The goal of the class was to help the city of New Haven analyze and make recommendations for how city planners and engineers stress and extreme hydrological conditions. Just as a little bit of a context here, cities in the United States are required to upgrade, update, and prepare sort of hazard mitigation plan every 5 years in order to be eligible for federal emergency funding. So we taught the class in a year when the city was about to update its hazard mitigation plan. So that's the broad the context. But under stormy weather, it's often get flooded. This is sort of a flooding hotspot. So this is how we structured the class. We structured the class according to activities and also deliverables of the class, making sure that those deliverables were relevant to decision making. So this is the analytical framework. It's simple, but is compatible with the kind of data available to the class at the time. So our idea was to basically map each important socioeconomic indicators and maybe also demographic indicators to come up with a simple vulnerability index or social vulnerability index map. And then we compare this vulnerability map with the map of weather climate hazard to identify vulnerable neighborhoods and then come up with appropriate recommendation for how to cope with the hazard. So this is the key result from the flooding groups. What I'm showing you here is basically the map of social vulnerability score from 0 indicating low vulnerability neighborhood to score of high indicating high vulnerability neighborhood. And superimposed on this map are 2 weather hazards, climate hazards. One is coastal flooding, shown here. Coastal flooding is basically taken from NOAA sort of flood sort of hazard website for Category 4 storm. Category 4 storm in New Haven is a 1 in 100 year event. So coastal flooding is not new. The information is not new to the city planners. What's new here is the those hotspots, inland flooding hotspots, we identified with a simple hydrological model and GIS analysis. And some of those flooding hotspots are actually located in high vulnerability neighborhoods. So that caught the city planners' attention. That became the focal point actually of the mitigation plan. So in that sense, it was quite successful. Now, when it comes to heat stress, the work was a bit harder because New Haven has not experienced catastrophic sort of heat wave event like Chicago or Paris. So we did quite a bit of research. We first find this epidemiological study that helped identify the heat stress, determine the heat stress threshold. According to this epidemiological study, if temperature goes beyond 30 degrees Celsius or 90 degrees, in the United States, we like to think in Fahrenheit, 90 degrees Fahrenheit, then the risk of mortality will go up rapidly. So we use 90 degree as the heat wave thresholds for New Haven population. And then we went back to analyze the weather data collected at Tweed International Airport, a weather station there. And we discovered, indeed, we have a very frequent heat wave events, and the frequency actually has been increasing over time. But of course, Tweed Weather Airport is not a good airport to represent the conditions in the city because it's located right on the coast and it's outside of the city. So to account for the urban heat island effect, the class decided just simply add 2 degrees Fahrenheit to the observed daily temperature. If you do that, you suddenly shift the frequency to a much higher value. So in recent years, we expect every year we expect 30 days of exceedance, days exceeding that heat wave threshold. So the stress, the heat, the hazard is real. And then we also did research going through newspaper archives, collecting anecdotes of extreme heat events happened in the past, hoping to sort of jog the memory of city planners, the older city planners, so make this hazard more relatable to their personal experience, right? And so this is one of the key results from the heat stress group. Again, I'm showing you the social vulnerability score map, but in a more condensed form now. And this is the heat map of the city, heat map from satellite observation of temperature. So this is an incredible high correspondence. You notice that. So city neighborhoods with high vulnerability are also neighborhoods with high temperature. At that time, it was a real surprise to us. But recently, my PhD student, T.C. Chakraborty, did a study of all the cities across the United States, and his team discovered, in fact, this pattern is actually quite common in the United States. But anyway, if we experience an extreme heat wave event, the situation might not be too bad if we have advanced sort of warning, because most of the urban residents are within walking distance to a cooling center. A cooling center is a public facility like a library or a church, a community facility like a church that has air conditioning, right? So with advanced warning, folks can go to those cooling centers and ride out the heat wave. Now, so a quick summary of this part of this case study. Nobody wants to experience extreme weather, right? But extreme weather turns out to be a useful impetus for action. So our recommendations for how to cope with flooding, inland flooding and coast flooding, were all adopted by the planners. But our because they still have that fresh memory of the devastation caused by a hurricane called Hurricane Sandy a few years before. But our recommendations for how to for dealing with heat stress were not adopted because, like I said, the city has not yet experienced a catastrophic heat wave event with hundreds of mortality. The second lesson learned is that best practices from other cities are often applicable to local problems. So you don't need to reinvent the wheel. So this best practice idea is part of this, what I call scalability sort of attribute that we strive to achieve when we move ahead. We start our urban initiative I spoke about a few minutes earlier. And then the third lesson is that short-term planning cycles, 3 to 5 year planning cycles, often conflict with the long-term commitment required for climate adaptation. And this tension will always be there when we talk about climate adaptation. So now let me move to the last part, the longest part of my talk, understanding and reducing urban heat stress. Like I said, this is an active area of research. I'd like to share some results with you from our work. And I want to begin with this cartoon diagram from Tim Oak's textbook depicting the phenomenon of urban heat island, right? So imagine you have a bicycle and you put a temperature sensor on your bicycle and you bike across this transect. Before you enter the city, the temperature reading will be stable and low. As soon as you enter the city, the temperature reading will climb up. And as you reach the city center, you would have the highest temperature. And the temperature difference between urban and non-urban land, rural land, is the urban heat island, right? A small increment of temperature. But some of you may wonder, why do we care about this tiny increment of temperature? Tiny by tiny, I mean maybe 1 degree, maybe 1.5 degrees of Fahrenheit. Well, it can change your heat wave frequency dramatically. So let's suppose this is the heat wave, the probability of temperature distribution in non-urban, in natural landscape. And then because of urban heat island, let's just simply say we shift the mean a little bit to here to represent urban temperature frequency distribution. Let's suppose this is the heat wave threshold. So for folks outside of the city, this is the heat wave frequency, right? This is basically the area under this curve, a small number. But if you look at urban landscape, the simple shift, because the simple shift mean the heat wave frequency now is much, much higher for urban residents. Furthermore, urban residents will experience record temperatures that's not been seen in non-urban land, right? So the phenomenon of urban heat island and the consequence of urban heat island, the health consequence of urban heat island are well known, are known for many, many decades, right? But it turns out it's actually very hard to predict the urban heat island intensity. So for a number of years, our group spent some effort trying to establish a predictive understanding of this phenomenon. So let me share some results with you. So this line of work actually was built on a theory we published about 10 years ago, a theory for describing, for predicting local climate effects of deforestation. One feature of this theory is what I call site pair or space for time substitution, whereby we envision a forest patch of land and an open land coexisting next to each other in the real world. In the modeling world, they are located in the same grid cell, okay? And they are subject to the same atmospheric forcing at the blending height. So in this framework, then deforestation signal is simply the temperature difference between open land, like a grass or cropland, and forest landscape, right? That's the deforestation signal. The other sort of feature of this theory is the distinction between radiative feedback and energy redistribution. Let me explain what I mean by that. When you deforest the landscape, you change solar radiation absorption, and then the long-wave radiation will adjust accordingly. That's called radiative feedback. You will also change two energy redistribution pathways. One is evaporation. Evaporation basically takes latent heat away from the surface and then deposit the energy above the atmospheric boundary layer in the cloud condensation process. The other pathway is convection, basically moving energy away from the surface to the lower atmosphere by atmospheric motion. And we introduced this new concept of biogeography called energy redistribution, using this sort of dimensionless parameter to quantify the efficiency of energy redistribution. So for example, if you go to southern United States, the energy redistribution factor is high because landscape there is dominated by trees and by forests. Trees are very effective convectors. But if you move to Western United States, in the semi-arid landscape, there the landscape is dominated by shrubs, by grass, by desert. And so those land features are poor convector of heat. So you see this kind of geographic distribution. And so the same theory can be easily extended. The theory developed for deforestation can easily be extended to study the local effect of urbanization. So urban heat island. So basically, this framework is just the temperature difference between urban land parcel and the adjacent natural land parcel, right? And so this is the predictive model that we come up with. The urban heat island intensity is basically a sum of component contributions from change in albedo. This is a reflectivity of sunlight, convection efficiency, evaporation, storage, anthropogenic heat, right? I don't have time here to explain all the symbols here, except to point out that F here is the energy redistribution factor I spoke about a few slides ago. So here's sort of a highlight, one key figure from our study showing you modeled and measured urban heat islands of US cities and also cities in southern Canada. And so we divide cities into three groups, according to the three climate zones. And we presented results for daytime and nighttime. This is a very busy slide, so maybe I should focus your attention to this panel. So this is urban heat island intensity detected by MODIS satellite. This is urban heat island intensity calculated by a climate model. This is the prediction we made with that theory I described to you earlier, and it's basically the sum of component contributions. Okay, so the conventional wisdom is that reduction in evaporation is the main contributor to urban heat island. And when you remove trees, you replace trees and grass with concrete surfaces, you basically remove that cooling potential, cooling by evaporation. So you expect higher temperature. But what we found was, at least for cities in eastern United States, southeastern United States, in this wet climate zone, the major contributing factor is actually loss of convection efficiency. So here, cities are not as efficient in convecting heat as the natural landscape. Natural landscape, as I mentioned earlier, is dominated by trees. Trees are very effective convectors, right? So loss of convection efficiency creates this warming. And interestingly, also, cities in this part of the country actually are brighter, have higher albedo than natural landscape. So albedo component itself is cooling. It causes cooling. Now, if you move to city group of city in desert, in semi-arid climate in Western United States, you find that convection role is flipped. There, urban landscape is actually more convective, is more efficient in dissipating heat to the atmosphere than the natural landscape in the daytime situation. Natural landscapes is basically short grass, shrub, and smooth surfaces. They are not very efficient at convecting heat away. So so it turns out that actually the role of convection actually cools the climate, cools the urban climate. So I want to show you this because I think it's very important to establish the mechanistic understanding, predictive understanding, before we can move ahead with strategies to reduce urban heat stress, right? So that's what I'm heading to now. I'm going to now talk about strategies with that kind of solid understanding, good understanding of the mechanisms that we think we are ready to develop strategies for reducing urban heat. So there are four sort of broad strategies for reducing urban heat stress. The first strategy is to use white roof. This is intuitive. Use or cool roof. Some people call that. By installing cool roof, white roof, you reflect sunlight away from your building to the atmosphere or even outer space, and so you end up with cooler interior. So your room will be cooler, and also you're going to cool the urban microclimate in general. The other strategy is green roof. green roof is not actually effective in cooling the climate. It has other societal benefits, but it's not effective strategy. I would not advocate this strategy for climate adaptation. And then the third strategy is the solar roof. This turns out to be actually my office building here at Yale. The south-facing side is covered by solar panels. So the solar panels work because instead of allowing a lot of the solar energy to be converted to heat, you actually capture some of the energy and convert that to electricity. So that's how it can create a little bit of cooling for you. And of course, the fourth strategy, this is a photo of Hong Kong, is to use street trees. Street trees brings sort of two kinds of cooling benefits, right? One is to generate evaporation, and by evaporating water from the soil, you expect cooling of the microclimate. The other benefit is convection. Trees, like I said, are very effective convector. They allow heat to be able to dissipate away from your street canyon to upper atmosphere. I want to now to draw your attention to the cool roof strategy a bit more, right? So here is a list of albedo values for different surface types for natural surfaces and also for urban surfaces, right? Urban surface has very varying a range of albedos. And the number we should pay attention to is the EPA cool roof specification. EPA has this ambitious goal of converting all the roofs to high albedo value with materials of high albedo value, about 0.88, 88% of reflectivity, right? And this number is for so-called white is white. This just came out 10 days ago, actually. Engineers at Purdue University invented this, what they call whitest white paint. And it's a near perfection. You know, it's almost near perfection. The albedo is 98%. If the engineers are able to make this kind of paint widely available and also make the paint durable, this is going to be a game changer in the climate adaptation arena. Now we did some calculations trying to quantify the effects of retrofitting urban surfaces to their cooling benefits of retrofitting strategies, right? This is what I'm showing you are results for US cities in summertime midday conditions. So right now, currently, midday rural background temperature in the summertime is 32.7 degrees. And urban temperature is, of course, a few degrees higher due to the urban heat island. This is surface temperature I'm talking about. At the end of the century, the background temperature will go up by 4 degrees by the model projection, and the urban temperature would also be higher than that. This is the future urban heat island intensity, right? Now, we want to be very aggressive here. We say, what if we replace all the roofs in all the cities with the cool roof material specified the EPA, sort of it's the satisfying the EPA cool roof specification? You would, if you do that, you bring a substantial cooling in the urban land. And then if you plant trees, you get a bit more cooling benefit. And then if you convert pavement like sidewalk and road to more reflective materials, then you get additional cooling. All those retrofitting strategies combined basically can erase not only urban heat island effect, but also the effect caused by greenhouse gas warming, right? So the cooling benefit is substantial if you are able to do all of those retrofitting strategies. Now, this is that's the average of all the cities. This is more spatially explicit modeling results. If you don't do anything to your urban landscape, this is the kind of urban heat island distribution you get for cities in the United States and Southern Canada. Here, each circle represents the size, the intensity of urban heat island. Some cities actually experience urban cool island, as indicated by the cold color here. This is, by the way, this is end of century type of situation. if then you implement EPA cool roof, then we basically turn all the cities into urban cool islands. The benefit of cool roof is not large at nighttime because, understandably, because we don't have sunlight to reflect right at nighttime. There are materials available, materials that have high emissivity, very, very high emissivity, available for retrofitting building roof. And so by having high emissivity, you allow long wave radiation loss, both in the daytime and at nighttime. So those kind of materials can also bring cooling at night. Now, I should point out, this is not purely academic exercise, not purely modeling exercise. This is actually a strategy being implemented. Cool roof strategy is being actually implemented by many cities. In this regard, Chicago is a pioneer, and in part, it was triggered by a devastating heat wave event that occurred in 1995 that killed nearly 1,000 people in a matter of a few days, right? So the city, after that catastrophic heat wave event, Chicago changed its own building code, requiring all new constructions and roof installation to use high albedo material. So about 10 years ago now, a School of Architecture student helped us to quantify the cumulative effect of that building code change to the urban landscape using satellite. So according to this analysis, the majority of the urban parcels experienced the increase in albedo from during this 15-year time period since the occurrence of that big heat wave. Averaged over the whole city, albedo increased by 0.02, a small but measurable increase over this big city, right? City of Chicago is very big. And so it translates to about a 0.5 degree of cooling, that albedo increase. 0.5 degree cooling could save a lot of lives in a heat wave event. And other cities are also following suit. For example, this is a news headline from BBC that came out 2 weeks ago. City of New York has embraced cool roofs as a climate solution. New York has installed, over the past few years, has installed about 10 million square feet of cool roofs. So that's about 1.5, I think I did an estimate, it's about 1.5 the size of University of Hong Kong. Of course, that's only a small fraction of the city, land area of the city. New York, of course, is huge, right? But it's a very important first step. Now, I want to help you visualize what an urban landscape would feel like if we do that kind of urban, so cool roof installation, right? So what I did here was I borrowed the sort of drone data, point cloud data generated by this company for the neighborhood in Switzerland, and then created this animation. So imagine you are a pilot or a bird flying around this landscape. This is what the neighborhood looks like. It's quite pleasant, right? You see a lot of roof surfaces. Now I digitally retrofit the landscape, basically going into the digital file and identify roof pixels and convert roof pixel to have high albedo value of 0.88. And this is what the landscape looks like. So it's quite alien, isn't it? I showed this animation to some visitors from Europe, from that part of the world, and all of them say they don't like it. They are not prepared psychologically to live in such a neighborhood. Now I have a few minutes left. Let me just explain to tell you where we're heading with this line of work. Basically, we are pursuing 4 lines of four directions. The first direction is to address this debate whether we should install cool roof or solar roof. Cool roof for climate adaptation, solar roof for climate mitigation, right? And so we did a set of model calculations. Again, this is for CDC in the United States. If you don't do any retrofitting, this is the amount of energy required for by air conditioning, okay? And then if you do cool roof installation, you reduce that energy consumption substantially. This is under current climate situation. And in future climate scenarios, you also see substantial energy saving. And so for reference, right, this is the EU residential building energy footprint. At nighttime, the cooling benefit is not large. And so then this brings the debate, are we better off using cool roofs to save energy, or are we better off to install solar roofs and to generate renewable energy and therefore reduce our reliance, offsetting energy use from fossil fuel consumption, right? So which is better for the climate? Keep in mind that roof space actually is a very precious resource in this regard. You can either do cool roof or solar roof. You cannot do both, right? And so the answer to that question is actually not trivial. It depends on geographic condition, climate condition, local climate conditions, and also depend on landforms, urban landforms. And so we are conducting designing a series of numerical experiments to help answer that question. So stay tuned. And the second direction we are pursuing is to answer the criticisms we have been facing with our work. Our work has so far focused on surface temperature. Surface temperature it can allow us to predict energy consumption. There's no question about that. But surface temperature, Earth's surface temperature, land surface temperature is not a good measure of heat exposure from the perspective of human health. A better measure of heat exposure is wet bulb temperature. And this is the technical definition of wet bulb temperature. I won't read that. I want to just point out that wet bulb temperature is different from dry bulb temperature or regular air temperature. Regular air temperature is a measure of internal energy, right? So according to our high school physics, it's a measure of internal energy or the kinetic energy of molecular vibration. But wet bulb temperature is an indicator of moist static energy of air. It's a more sort of a thermodynamic variable describing air motion. And this is how you measure wet bulb temperature. You basically have a regular thermometer and you cover it with wet cloth, allow it to sweat, so to speak. And the temperature you measure with the thermometer is wet bulb temperature. So in a way, wet bulb thermometer is a physical analog, a physical model of a human skin. So wet bulb temperature from the perspective of human health is really the lowest temperature human skin can be cooled to by sweating. Okay, so that brings me to this lethal threshold. So we human, you and me, humans are warm-blooded animals. We need to maintain our deep body temperature, the temperature of our vital organs, the heart, the brain, at a constant of about 37 degrees Celsius, right? In hot environment, our blood vessel will dilate to allow heat to dissipate, heat generated by metabolism, metabolic heat to dissipate to the environment, right? And so in hot climate, sweating is actually the only way of maintaining low skin temperature. A fan or ventilation would not do the trick for us. And in order to allow the heat to dissipate from metabolic heat to dissipate away from our body to maintain a constant deep body temperature, we need to have a 2-degree difference between the skin and the deep body. In other words, your skin temperature, our skin temperature has to be lower than 35 degrees, right, degrees Celsius. So if wet bulb temperature of the environment goes beyond 35 degrees, then this difference can no longer be maintained. It's no longer possible without cooling, without artificial cooling, without air conditioning. And so if we subject ourselves to that kind of lethal temperature, eventually our body temperature will go up and we will die. So we are developing some research here. We introduced this new definition of heat island called wet bulb urban heat island. Basically, it's just the difference in the wet bulb temperature in urban land and the wet bulb temperature of adjacent natural land. And here's our hypothesized patterns of wet bulb urban heat island. We expect urban land to have higher wet bulb temperature, and some of that comes from convection, the air motion. Some of it is contributed by what we call diabatic heating, energy input. And the daytime and nighttime patterns are different. This sort of hypothesized patterns are basically confirmed by modeling calculations. And we are now in the process of validating this pattern with observations on using mobile instruments I will describe to you in just a moment, using sensors mounted on bicycles. So that's the second direction we are pursuing. And third direction we are pursuing is to address this business of synergistic effect between high temperature and urban heat island. So earlier I described urban heat island as a phenomenon of simple shift in mean state, right? Like so, but reality might be more like this. You not only experience a simple shift in mean, but also you expect a change in variance, an increase in variance. In other words, you expect in hot days and hot weather, you also expect stronger urban heat island. So in other words, urban residents will suffer double damage, right? Because of the compound effect of high temperature and stronger urban heat island. So we are quantifying this synergistic effect and describing this pattern across different geographic zones. So that's one the third direction we are pursuing. The final direction I want to share with you is about this new project that is in its first year of implementation called Biking for Science and Health at Yale. This is a project that draws expertise from a number of departments and units across the university. And the goal is to integrate smart sensor technology with public and private bicycles for urban environment monitoring. A big part of the goal is to monitor urban heat stress across different, in a very, very fine scale across different landscapes. We also want to monitor pollution level and as well as carbon dioxide concentration across the city landscape. So the team has, our team has made us a lot of progress, and my only contribution here is the design of this logo here for the project. My team members liked it. I hope you also like my design for this project. So here's the sort of conceptual diagram of the project, right? So we like to design sensors, mobile sensors. Sensors can be deployed in large quantity and very inexpensive. And so some of them will be on private bicycles, so basically turning cyclists into citizen scientists collecting data for us. And we also need to use their smartphone for geolocating the measurements and for retrieval and transmission of data. We'll also, in the next phase, we also want to implement sensors on public bicycle fleet. When a bicycle is returned to a bike station, the data then will be transmitted to our router, and the router then will relay the data to our server for analysis and archival. Right. So that's the overall design. We have some success. We have this sensors now in operation. This is what we call smart T. T for temperature. Smart T temperature and humidity sensors. They are very robust, very inexpensive, very low power consumption. And this is what it looks like. This is the dimension of it. This is what it looks like when you put it on a bicycle. This is the phone app allowing the cyclist to geolocate the data and to also communicate with the device for data collection. And so we are now in the phase of designing smart P for measuring particulate matters, smart O for measuring ozone, and also smart C for measuring carbon dioxide. Now, just to quickly share you with a snapshot of the kind of data we are collecting with this kind of sensors. We have a lot of collection here in New Haven, but we also have volunteers in many other cities collecting data for us as well. So you see clearly a very nice pattern tied to the urban morphology, right? So predictable pattern. And then this is a comparison of the same data, biking data, with MODIS satellite retrieved surface temperature. Many of you know MODIS satellite measurement has very coarse resolution when it comes to surface temperature. It's the resolution is about 1 kilometer in size, right? So we came up with a geospatial modeling technique that allows us to sharpen, so to speak, MODIS temperature to 60 meter resolution, and then we then collect data along the bicycle transect and compare with the air temperature measurement with the mobile sensors. They are not exactly the same, but they are. You see a very high correspondence. So that raised our hope that by combining this kind of mobile measurements with satellite monitoring and also with characterization of urban morphology, we should be able to come up with a very good predictive model to map urban temperatures across the urban landscape or neighborhoods. There's also a plot for wet bulb temperature, and dry bulb temperature look very different. I don't have time to explain to you. So let me now, I'm at 1 hour mark. Let me just conclude here with a few sort of messages. First of all, we think sensible climate solutions should be scalable. I have not spoken too much about scalability here, but the idea of best practice, as I said earlier, is part of this scalability, so attribute, right? So those solutions should be scalable, but should also allow for variations in local geographic context and urban developmental stage. So that's the first point I want to make. And the second point I want to make is that, and that's by my personal opinion, that urban heat stress perhaps is the biggest climate threat to society, perhaps even bigger than sea level rise. Let me explain why. The urban heat stress will reduce outdoor labor productivity substantially, and it will increase the AC energy consumption, and AC energy consumption, of course, will amplify local urban heat island because of the waste heat it generates. It also will amplify global climate through the consumption of fossil fuel, right? And in places where you don't have access to AC, like those informal settlements, and under extreme high temperatures, you expect a mass migration. And then the third point is that we should be aware of trade-offs between mitigation and adaptation. The debate about whether to use solar roof or cool roof is one aspect of that. And the point here is that in order to move forward with climate solutions, we need to strike a clear, careful balance between mitigation and adaptation. We need to move on both fronts simultaneously. And finally, we are very excited about the smart and distributed sort of sensor technologies, new sensing technology, and we believe that the new technology may contribute to a paradigm shift in urban climate modeling and in also urban greenhouse gas monitoring. So with that, I will stop here and entertain questions.
Thank you, Professor Lee, for that very inspirational presentation. I certainly learned a great deal, and I'm sure that my colleagues and fellow students would be thrilled and be inspirational as well. So may I now open the Zoom floor to take any questions and comments? Before that, may I take the my advantage of being the moderator to ask Professor Lee to ask you questions. At the very beginning, you highlighted two different forms of urbanization. You call horizontal, or what I may call extensive urbanization, and the other is vertical, or what you call compact city, right? Now, I mean, you have presented your research result from New Haven. That is, could be taken as characteristic of horizontal urbanization. Now, when we come to Hong Kong, obviously we're looking at high rises, so that could be taken as characteristic of vertical urbanization or compact city. My question then is, when we talk about urban heat island effect, what difference does it make between these two types of urbanization?
So Professor Lin, you touched on another sort of trade-off between mitigation and adaptation, right? A compact urban form, a lot of people argue, like Hong Kong, with a lot of high-rises, are more energy efficient. And therefore, from mitigation perspective, that's the kind of form you want to have. But then, compact form of urban landforms also generate a lot of urban heat, more concentrated urban heat, I should say, and therefore you expect a stronger urban heat island. If you go to New York City, for example, downtown New York City, Manhattan, the urban heat island is really, really strong because of the compactness of urban living there. And the other aspect is that when you have a compact form, the idea about retrofitting doesn't work as well. Retrofitting roof doesn't work as well because you don't have a lot of roof surfaces to work with in a more compact form. So you have that tension there between mitigation and adaptation. You are trying to strike a trade-off, a balance of trade-off. So that's a difficult trade-off to try balance to strike.
Okay.
But very important though, from the consideration of moving cities forward.
Thank you. May I invite John Bacon-Song, Professor John Bacon-Song, to ask your questions? John?
Hi. Thanks very much, George. So it's a fascinating presentation. There's actually a Hong Kong U Cambridge project looking at smart sensors in the context of air quality, where the calibration effect, if you like, is the government air quality monitoring stations and using big data. So that seems to link very nicely, potentially, with what you're doing on temperature and humidity, if I understand it. But my question is really about air quality. You didn't really mention air quality much. So if the air quality is poor, does that mean that the albedo effect is not as helpful in terms of improving the roofs?
Okay, there are somewhat, by the way, we are also developing air quality sensor. We'll have the first prototype ready to monitor PM 2.5 and PM 10, maybe in a couple of weeks. Anyway, to come back to the question about air quality. So albedo effect only targets temperature. So when we put a cool roof, shiny paint, the whitest white paint, so to speak, right, on top of roof, we are basically reflecting sunlight away from your urban landscape to the outer to the outer atmosphere or even outer space. Some of it actually can escape to the outer space. So by doing so, we reduce urban temperature. So that will benefit from health perspective, especially on the heat wave event. But there is a little bit of shall we say, side effect when it comes to urban air quality. When you reflect sunlight away, you basically reduce the convection in the urban landscape. You basically shrinks the so-called boundary layer thickness. And you end up with a lower sort of ventilation volume, so to speak, in terms of air quality modeling. That's an air quality modeling jargon. And so same amount of emission of air pollutants can actually accumulate a bit more in urban landscape. So you may increase air pollution level because
my question was sort of the other way around, in the sense that the air quality was poor, would that reduce the reflectivity?
Oh, I see where you're going. Yeah. That's okay. So basically, you're saying if the sky's hazy, right? If the sky's hazy, then albedo effect will be reduced. Yeah, that's true. So when you have hazy sky, then your albedo, the white roof will not be as effective. Or you can put it to an extreme situation when you have overcast skies. When you like in a cloudy place, like in a place where you get clouds all the time, then that albedo effect is not as effective. So it's very much local context specific. And so it's not a one size fits all.
Thank you.
Thanks for that question.
I got another two questions. So one is from Mr. Zhong Sayer. Mr. Zhong Sayer, could you raise your questions?
Sure. Thank you. A very, very interesting talk. Given the talk about the problems and the dangers of wet bulb temperature, my question is simply, in cities that naturally have higher humidity, like Hong Kong, does this mean that climate change and global warming pose more of a health risk as temperatures rise slightly than cities, say, in more arid regions like the Middle East, which may have higher overall temperatures but are much drier, and therefore the wet bulb temperature is not so severe?
So it turns out in Middle East, if you look at the coastlines, actually those cities are in danger because they have the humidity coming from the coast. But if you are moving more into interior location, you're right. Those cities are safer. And so this is a very difficult question. That's sort of is more of the frontier research in terms it comes to climate assessment. Now people are now moving towards, instead of relying simply on temperature, on dry bulb temperature, people are moving towards wet bulb temperature. And if you look at wet bulb temperature, a lot of our wisdom may get overturned. In the past, people say, well, we are going to experience extreme faster temperature increase in northern cities. But then if you look at wet temperature, maybe we should more worried about cities in tropical, subtropical latitudes, right? Hong Kong being one of those. And that certainly is a worry. And so we are, a lot of people are now moving towards this direction using existing climate data. Believe it or not, we actually don't have a very good understanding of wet bulb temperature distribution, extreme wet bulb temperature distribution under current climate conditions. So people are now using climate data to help us establish that baseline, and then we are now also pushing the modelers. So this is another thing. If you look at last generation of climate model results, they don't archive data so that you could calculate wet bulb temperature. And that's changing. That's changing. The next generation of climate models, the CMIP6 climate models, modelers are now more conscientious of this demand, this requirement. They are archiving data so you can actually compute wet bulb temperature under future climate situations.
Okay, I got another question from my faculty dean, Professor Will Hayward. Mr. Dean, would you like to raise your questions to Professor Lee?
Hi, Shui. Thanks for a great talk. Really enjoyed it. I really enjoyed also the virtual revisit to New Haven as well. That was very enjoyable. Yeah, I'm interested in, you know, one of the things that cities have to do is to continually redevelop, right? And in Hong Kong,
Right.
there's this continuous tension as a place like Hong Kong, which has no available space, essentially needs to find new space. There's a tension between reclamation. Obviously, that's been a historic strategy and continues, and there's a plan for a massive new reclamation just in the sea, kind of between Lantau Island and Hong Kong and Kowloon, or, you know, redevelopment of, say, brownfield sites, you know, old industrial areas, farmland, so forth. I just wonder whether your models have anything to inform about whether those strategies or other strategies for redevelopment are best or create the biggest problems for, you know, heat stress.
So I should admit that the model right now is, like I said, is very crude. The model that we used is NCAR climate model I touched on briefly. So there you have a subgrid representation, but you lump everything together. So you cannot resolve neighborhoods. You can only say, okay, in fact, you cannot distinguish cities, actually. So the grid cell representing, say, Connecticut would lump Bridgeport, Hartford, New Haven all together in one blurb of a city, right? So this model is clearly not suitable for addressing the questions you raised. But there is hope, perhaps by doing nested modeling, by downscaling, that we might be able to test some of the strategies. The nice thing about modeling is that you can implement numerical experiments, right? You can experiment. You can build a building and paint the roof, and then you feel like, oh wow, they are not working. Then you can just remove the building and remove the paint and paint it again without any regrets. You can't do that in a real situation. So to support that kind of city planning effort that Will you described, we need a model that's capable of doing that kind of numerical experiments, a model that can resolve a neighborhood scale, even down to a blocks level, about, you know, whether to build the brownfield or to retrofit, or if you retrofit, say, how to retrofit the buildings. After all, once you build a building, you are locked in, right? You're locked in for many, many years, many decades. So you need to figure out a way of for old buildings, you need to figure out a way of doing retrofitting to benefit the climate. Or if you are building on a brownfield site, you know, come up with the most sensible strategy forward. And I think modelers have a great responsibility here, a great role to play. But current models are not adequate.
Thank you. Professor Paul Ip. Professor Paul Ip. Paul?
Yes, thank you for a very good, excellent talk. Just wonder, I think now we always bring in this social return on investment. You know, after you implement on this measure and then the added value, I think on the environment, the climate. Have you ever considered this? I mean, this cost-benefit analysis. I think in all this wonderful effort, I mean, to improve the environment, improve the living standard of the city.
So I want to be honest, that's outside my field of expertise, but that's I think very, very important. You know, I mentioned earlier, right? For example, when I'm a simple climate scientist or geographer. So when we talk about green roof, I mentioned green roof, and from the simple perspective of urban